All right, third time's the charm. This is actually my third recording. Here we go. So in the class, we left off discussing which elements are found in living organisms. So of all the elements on the periodic table, 90 of them occur naturally on Earth. 12 of those are found in living things that are above the trace amount level threshold. So of the 12, 4 of them pretty much make up the bulk of it, and that is carbon, hydrogen, oxygen, and nitrogen. So you can see that these are the 12 that are found in living things, and the bulk of it, CHON, comprise of 96.3% of your body weight. Now, phosphorus and sulfur are also very important because phosphorus is found in DNA and sulfur is used in a lot in proteins. So I would actually argue like these 6 are very, very important, and these would be considered the trace amount levels. Okay, but organic compounds are compounds that contain carbon, and you can see that carbon is really responsible for like nucleic acids and carbohydrates, obviously, lipids and proteins, and you can see all the other sub-molecules that can be made from that. So there's actually a pretty cool flow chart of organic compounds found in living things. All right, so that was section 2, elements found in living things, related atomic structure to the periodic table of elements, and then list the important elements found in living things. Moving on to section 3, the nature of chemical bonds. So we're going to go back to ions, positive charge or negative charge, cations or anions, and then look at how molecules are formed when they join by covalent bonds, and then contrast polar and non-polar covalent bonds. So there's actually 2 types of covalent bonds that we can look at. So let's tackle some vocab here. First off, what is a molecule? A molecule is a group of atoms held together by energy in a stable association. And these groups of atoms, they can be the same, like 2 hydrogens or 2 nitrogens, or they can be different atoms. So H2O, 2 different elements, 2 different atoms held together by energy in a stable association. This is glucose, C6H12O6, 3 different elements, 3 different atoms. Now, a compound is when a molecule contains atoms of more than 1 element. So these examples up here that are in blue are examples of compounds because I have 2 or more different elements found in that molecule. These are not compounds because they are comprised of the same element. So I think there's a saying out there that goes, all molecules are compounds, but not all compounds are molecules. Okay. Now there are 2 types of bonds that we're going to focus in on. Ionic bonds, which I've briefly covered in the previous sections, when electrons are being transferred, like sodium and chlorine, how sodium just gives up that 1 electron to chlorine so they can both be happy and have filled outer energy levels. In those cases where electrons are being transferred or taken, we call them ionic bonds. Now, there was a question raised yesterday in class, like, well, why does carbon just have 4? How come there's no plus or minus? Well, in that case, they tend to share electrons. And so sharing really doesn't produce any charges, so we call that covalent bonds. But let's take a look at ionic bonds. So ionic bonds form crystals, and you can see that we form this nice little crystallated structure of positive and negative. And this is actually how ionic substances form. They arrange themselves based on their charges. Opposite charges attract, and they form this nice little crystal structure. That's why you find like the salts, like sodium chloride and magnesium chloride, and I don't know, yeah, you just find them in crystal structures, and sometimes they're nice little like cubes. But ionic bonds result when these atoms of opposite charges attract, and then electrons are transferred or stolen. They are not shared. So these are all great examples of ionic bonds or ionic substances. It results in an ionic compound that's electrically neutral. So 1 positive charge, 1 negative charge, put them together, they're neutral. Now, calcium on the periodic table has a +2, and chlorine has a -1. But because I have 2 chlorines, that means I have an overall net charge of -2. So +2 and -2, they are electrically neutral. The attractive forces between this sodium exists in all neighboring directions. So you can see that it is completely surrounded by chlorine. So a fun way to remember ionic bond. The name's bond, ionic bond, taken, not shared. So that's ionic bonds in a nutshell. When we get to chemistry, sorry to my 2 seniors in this class, but when we get to chemistry, we'll spend more time on this, a significant amount more time talking about ionic bonds. All right, so covalent bonds, electrons are not going to be taken or transferred, they're going to be shared. And they can share one or more pairs of these valence electrons. And so remember, electrons in the outermost energy shell, those are valence electrons. So some examples of covalent compounds, or molecules in this case, H2O2, N2. Now, molecules in covalent bonds are stable for a couple different reasons. First off, there's no net charge. Okay, it's just neutral. The octet rule is satisfied for both atoms, and it also has no unpaired electrons. So you can see here that this is a very rude picture, like a crude, not rude. This is a very crude picture of, let's just say, hydrogen. So I have one proton and one electron, and so they need, like this hydrogen atom needs one more electron, and this hydrogen atom needs one more electron. And they're like, hey, let's share. So they form a bond, and now this electron sometimes goes over here, and then it goes back to its original, and vice versa. And now we have a shared bond, like a connection where they're sharing electrons, and as a result, you get a covalent bond. So chlorine over here, it needs one more electron. This chlorine needs one more electron. They say, hey, let's share these electrons so we can both be happy, and now a covalent bond has formed. Now, the strength of covalent bonds depends on the number of shared bonds. So single bonds are the weakest. You can have double bonds where they share 2 pairs of electrons. You can have triple bonds where they share 3 pairs of electrons. And so you can kind of see this down here with our rudimentary Lewis structures, just showing 2 pairs of electrons being shared and 3 pairs of electrons being shared. Now, molecules can have several covalent bonds within them. So here's methane, CH4, and you can see that it has 4 covalent bonds. Okay, so there's methane. Oh, this is where I usually draw. I don't think I can. No, I can't. C2H5OH. So if you could picture, draw C and a C and connect the two. And then on this first C, literally have 3 branches coming out and put 3 hydrogens. And then on the second C, put a branch on top and on bottom and put H. So now these are all accounted for. Now on the second hydrogen, have a branch going off in this direction, hooked up to an oxygen, and then have that oxygen hooked up to a hydrogen. So there's lots of covalent bonds going on there. Okay, but anyways, there is a difference between polar and nonpolar covalent bonds. So covalent bonds means that they share, but we all know that sharing is not always equal. Okay, like if I bring in a pan of brownies and I cut this pan of brownies into equal pieces, all right, I'm sharing equally. But I could bring in a pan of brownie and just literally like cut it into really, really, really small pieces and save me a big slice for myself. I'm still sharing, but I'm not sharing equally. And so that's what polar and nonpolar means. So electrons are being shared, but how equally are they being shared? So in this case, for nonpolar covalent, that means they're being shared equally, okay? Whereas for polar covalent, yeah, they're not being shared equally. So how do you determine whether or not it's going to be polar or nonpolar? You have to look at the electronegativity value. And I'm not sure if your book has a table of the electronegativity values. I'm pretty sure it does somewhere. But these are electronegativity values. And these numbers mean that the higher number you have, the more prone you are to being like an electron hog, if you will. So the nucleus that is more electronegative or has the higher value has a greater pull on electrons than one that is less negative. So fluorine is the Mac Daddy of them all with 4.0. Oh, shoot, let's go back. And these guys down here have very low values. And so if if they were to bond with fluorine, fluorine's going to be hogging all those electrons, or those electrons are going to hang out with fluorine more than they would with the original parent atom, if you will. So electronegativity tends to increase from left to right as you go across the periodic table, and decreases down in the columns of the table. So highest electronegativity values, lowest electronegativity values. So nonpolar means that the affinity for electrons is the same. The electrons are shared equally. Polar means that they are being shared unequally. And a lot of times you'll see in diagrams and books this little Greek delta symbol. It's like an S, but it kind of curls itself back up. So here I have chlorine and hydrogen. And if I go back to this slide, chlorine is 3 and hydrogen is 2.0. So that means that my chlorine is going to be slightly more negative because the electron of hydrogen is going to be hanging out with chlorine more than it is with hydrogen. So I have a slightly partial charge negative and a slightly partial charge positive because hydrogen kind of, I don't want to say lost that electron. It's just not hanging out with the electron as much as it should. So that's what it means by partial charges. So you can have partial charges between molecules. In this case, 2 hydrochloric acids, and this is water. And this is actually really, really important because it's actually going to form a hydrogen bond. And we'll talk about that, I think, in chapter 2. So this is CO2, okay? So carbon has the lower electronegativity value of 2.5, and oxygen has a 3.5. So the electrons of carbon tend to hang out more with the atom or the nucleus of oxygen. So as a result, oxygen has a slightly negative charge because those electrons from carbon are hanging out with it, and carbon tends to have a slightly positive charge because it, lost. And like I said, I don't want to say lost, but those electrons are just not hanging out with carbon as much as it should. Now, chemical reactions, when they do occur, tend to break and reform bonds. They alter bonds. And so basically you're shifting electrons from one atom to another, or bonds are just kind of being broken. And my picture cut off the word identity here as I'm reading this out loud in my head. So chemical reactions involve shifting of atoms from one molecule compound to another. Basically, you're not changing the identity of the atoms. You're just breaking bonds and reforming them. And maybe you're creating polar or non-polar covalent bonds in the process. Okay, but if I were to count up, I would have 6 carbons on this side and 6 carbons on this side. I'll have 18 oxygen atoms on this side. 6 times 2 is 12 plus 6 when I do my little FOIL, or distributed. It's not FOILing, it's distributed. That equals 18. Over here I have 6. 6 times 2 is 12. 12 times 12 plus 6 is 18. And then I should have 12 hydrogens. 6 times 2 is 12. And then over here, boom, 12 hydrogens. So I'm following the law of conservation of mass. I'm not creating or destroying or throwing in a phosphate or sulfur or whatever. I'm using what I have and just rearranging it to make new products. Now, there are 3 very important factors that determine or help, well, what am I trying to say here? But there are 3 factors you need to be aware of that can affect the rate of chemical reactions. First one is temperature. If you increase a solution, temperature helps to kind of jumpstart chemical reactions. And the reason for that is when temperature increases, you're given energy to those atoms, and atoms, when they gain energy, they tend to move around a lot faster. And so this heating causes more collisions between those atoms. The second thing you need to be aware of is concentration of reactants and products. If you have a lot of reactants, things that go into a chemical reaction, then it may flow from chemicals to products. But if you have a lot of products and not a lot of reactants, it may be slower. So just be aware that concentration of what you have can affect the rate of your chemical reaction. And then finally, catalysts. Catalysts are substances that do not partake in the chemical equation. They are not products. They're there and they're chaperones, and they help the reactants find each other, and then the reactants find each other and the chemical reaction occurs, and then the reactants are just left in that solution. So actually when we do our liver lab, or when we did our liver lab last year, if you remember, we were looking at a catalyst to help jumpstart the reaction between hydrogen peroxide and liver catalase. So there's section 3, nature of chemical bonds. Section 4 deals with water, which is a very vital compound, especially to life. So I'm going to talk about hydrogen bonds, talk about some properties of water like cohesive and adhesive, and as well as some other properties that are associated with hydrogen bonds. Then talk about the relevance of water and their unusual properties and how they relate to living systems. And then talk a little bit about dissociation products of water, because water can break down into its parts and then reform. So in the beginning of life, water literally provided a medium for molecules to move around and interact. In fact, life probably started in water, in the oceans. And so life evolved in water about 2 billion years before spread into land. So life is tied to water. If you think about ourselves and all living things, most organisms are made up mostly 2/3 water. And so we require a water-rich environment, either internally or externally, for that growth and reproduction aspect. Now, the structure of water is bent, and it's made up of 1 oxygen atom and 2 hydrogen atoms held together by single polar covalent bonds. Now, the word polar means that these electrons are being shared unequally. And as a result, I get slightly partial charges. So oxygen tends to be slightly more negative because it has a higher electronegativity value. And hydrogen tends to be slightly positive because the electron that it originally had is now hanging out with oxygen more than it is with it. So sad. So as a result, we get something called a dipole moment, where I can take this molecule and literally cut it in half and have a negative end. I can cut it right here and have a negative end and a positive end. And water can act like tiny little magnets. So that's kind of cool, dipole moment. Not only that, water is bent. If water was linear, would I be able to cut that molecule so I can have a positive end and a negative end? And you should be saying no, absolutely not. And that's what happens with CO2. If I go back to CO2, right there, bam. Here's CO2. CO2 is linear. Okay, I have a negative, and then it goes positive and negative. So I can't cut this molecule and be polar. So that's why it tends to be non-polar right here. Now, if CO2 was bent like water, then it would be polar, because I can cut it and I can have a positive end and a negative end. But because it's linear, I cannot. So it's a good thing water is bent. And the reason why CO2 is linear is because of those double bonds. Double bonds are a little bit more rigid than single bonds. Okay. All right, so water is a pretty stable molecule. There's no unpaired electrons or any net electrical charge. And water, because of its dipole, the positive end and negative end, literally acts like tiny little magnets, and they can interact with other water molecules. And how they interact is through hydrogen bonds. So the partial negative charge on an oxygen interacts with the partial positive charge on a hydrogen of a adjoining or nearby water molecule. Now, hydrogen bonds are weak. Okay, it's not a full-on chemical bond where electrons are being transferred. It's just like an attraction. So they're very, very weak. But when you have a lot of water molecules, these hydrogen bonds can be actually pretty strong. And they are responsible for a lot of properties that are necessary for life. First off, your DNA is held together by nitrogen bonds. Okay, the A, when it pairs up with T, is actually held together by 2 hydrogen bonds. The G and the C is actually held together by 3 hydrogen bonds. So these dashed lines represent hydrogen bonds, and you can see that water is interacting, these water molecules are interacting with each other. So because these water molecules are interacting with each other, they actually can rearrange themselves into a crystalloidal structure. And this is why ice tends to float. When water molecules actually slow down and arrange themselves and become solid, there's like microscopic air pockets, and these water molecules are less dense and they float. And that's actually really important, especially in Minnesota. Ice forms from the top and works its way down, because it was from the bottom and worked its way up like it does in other substances when they freeze. We really wouldn't have life in our lakes. So at moderate temperature, water is a liquid. And because they have attraction for each other, we call that cohesion. Cohesion results in surface tension, basically the tautness of the surface of a liquid. So if I looked at my water molecules, like from the side, you can see that they're interacting with each other, okay? But at the top, they form stronger bonds, and so this is called surface tension. And this is what allows insects to walk on water. Now you may remember in biology how we could disrupt the hydrogen bonds, the attraction between each water molecule, and all you have to do really is introduce a nonpolar molecule, like soap. Okay? If I put a drop of soap, these interactions break down, they don't occur anymore, and this poor little water strider is actually going to drown. Okay? All right. I don't know. So this is called cohesion. Water attracts water. Sorry, I don't know why I didn't put that first. Weird. Okay, and I did it for this one too. Awesome. So adhesion is when water is attracted to other polar objects and molecules. So water is attracted to itself, but it's also attracted to other polar objects. And this is where we get a nice little meniscus going on here. So when you pour water and you look at it from the side, you can see that it tends to dip below, and that's because these water molecules are actually trying to climb up the side of this polar container. So it explains why substances contained in polar molecules get wet when they are immersed, and then hydrogen is responsible for this climbing up the sides, and we call this capillary action. Super important in plants. This is actually how plants get from roots and work their way up to the very, very top. I mean, just think about our huge redwood forests of California. Hopefully none of them are burning, but if they are, yeah, rip. Anyways, capillary action is how water moves in plants, so very important in life. Now another property of water, high specific heat. So I've talked about cohesion, adhesion. Here's the third property, high specific heat. So these hydrogen bonds can absorb heat when they break, and as a result they can release heat when they form, and they help to minimize temperature changes. Water is tend to use as like a heat sink. It can absorb large amounts of energy before the temperature changes. So this helps us maintain our body temperature, helps us maintain that 98.6 degrees, helps keep our cells from being destroyed when it undergoes chemical reactions, because when it does cellular respiration, that's basically a combustion reaction, and it helps absorb some of that heat so our cells don't fry. Another property of water you should be aware of is high heat evaporation. So the evaporation of water results in cooling of the surface. Another property, solid ice is less dense than liquid, so it floats. And then solubility, how water is polar. Sorry, an alarm going off here for a Zoom meeting. Water is polar and considered the universal solvent. Give water enough time and it probably can dissolve everything. However, it does not interact with nonpolar molecules like fats, oils, waxes. Tends to beat up when it interacts with those types of substances. But as a result, water can help organize nonpolar molecules, and we call this hydrophobic exclusion. And maybe this is why cells tend to be spherical in shape, because our plasma membrane is made up of hydrophobic molecules, and they don't like water, so they tend to hang out with each other and form spheres. Now, covalent bonds of water can break spontaneously. So if I have water at 25 degrees Celsius, 1 out of every 550 million water molecules will break spontaneously. And so what happens is I just kind of have a proton, aka hydrogen, floating around, and an OH group on the other end just floating around, but then they can find each other and reform bonds. So that's what water dissociation is. Next, water can form ions. Why did I do that? I do not know. Okay, so some pictures just showing some of these properties of water, how water has a very high heat capacity. It can absorb large amounts of energy before undergoing temperature changes. So you can kind of see copper, which is a metal, can change temperature very quickly. Granite, which is a rock, can also change temperatures really quickly. If you remember, I think, was it 2 years ago where my room was ice cold and I just took rocks and I heated them up, and actually I want to say it was last year, and just, here, put this in your pocket, keep warm, etc. Here's water forming that crystallated structure, nice floats. Here's water breaking down ionic substances, and you can see that these water molecules, the O negative is interacting with the positive ion, in this case sodium, and the hydrogens that are positive are hanging out with the chloride ion, which is negative. Here, this is probably my favorite part of a car wash, when they spray on the wax. So you're sitting in the car and you're going through the rinse, and your water on your windshield looks like this, but then they spray the wax on, and then it just all beats up. It's so cool. Okay, so that does it for section 5, water as a vital compound. We talked about the structure of water and how it leads to those hydrogen bonds because it has that slight polarity, it's dipole, how water tends to stick to each other as well as stick to other substances because they're basically like tiny little magnets, how hydrogen bonds affect all the properties of water, and how water pertains to life for those systems, and then water can spontaneously break down. Moving on to the final section, acids and bases. Define acids and bases as well as the pH scale, and then relate the pH changes in regards to concentration of hydrogen. So, concentration of H ions and hydroxide ions are described as acidity and basicity. I said that wrong, but you know what I mean because you can read. Pure water has a concentration of hydrogen at around 1.0 times 10 to the negative 7. So here is the pH scale, 1 through 14, right? And neutral is in between, 7. Now you notice that this is a logarithmic scale, or maybe you don't notice, but it is, and that's why I have this times 10 to negative 7. So if you just look at this exponent here, 7, neutral. Now remember I said water is not completely stable. I mean it is, but it's not. It can dissociate. It can undergo chemical reactions by themselves. So this is the dissociation part, where water can spontaneously break down into a hydrogen ion and a hydroxide ion and vice versa. So this is a reversible action. It can go this way and it can also go backwards to form water. Now a hydrogen ion is simply a proton. So if you ever say, oh, a proton is released, really we're just talking about a hydrogen. Substances that give up protons during chemical reactions are called acids. Molecules or ions that acquire protons, gain protons, are called bases. And so as a result, it's almost like a redox reaction, reduction oxidation, but this time we're looking at protons. We call it an acid-base reaction. So redox require electrons, donors, and electron acceptors. But with acid-base, we're looking at the transfer of protons. Now, in reality, protons never really ever exist by themselves. Like I said, if you take a look at water, I said, oh, you'd have an H plus an OH, and it can go backwards. Really, it forms an H3O plus, and it can go back. So it will just find another water. That lone proton will just find another water molecule and form H3O. But that's pretty technical. You need 2 water molecules to do that. So, yeah. But if you notice that this chemical reaction is balanced, yes, I have 2 hydrogens and 2 hydrogens for a total of 4. 3 plus 1 is 4. I have 1 oxygen and another oxygen for 2 oxygens, and over here I have 2 oxygens. So water can act as both an acid and a base, depending on the situation that it is in. So we use the pH scale to measure that hydrogen ion concentration. And like I said, it's a logarithmic scale. Pure water is neutral because H plus equals OH negative. If the value of your pH is less than 7, it's acidic. If it's more than 7, then it's basic. Now the thing about the log scale is even though you have a substance that's a pH of 4, and you have another substance of pH 5, it's not just one more, it's actually 10 times the hydrogen concentration. So if I went from 4 to 6, you go 10 times 10 for 100. If I went 4 to 7, it'd be 1,000. So just keep that in mind. All right, let's take a look at some properties of acids and bases and comparing the two. So acids are any substance that dissociates in water. Basically, you're increasing your H plus ions. The stronger the acid, the more H plus ions are produced. So if I have the stronger the acid, I have more H ions. Now this is where people get tripped up. More H ions means your pH is lower. So the lower your pH, the stronger your acid. Stomach acid is a great example, HCl. Okay. Now bases. A substance that combines with protons because they acquire or gain, and then acquire protons when dissolved in water. Thus, it lowers H pluses. We call them basic or alkaline substances when the pH value is above 7. So anything above 7 is basic or alkaline. And a lot of times bases are associated with cleaning substances like ammonia and bleach and sodium hydroxide. All right, so inside of us, we have a lot of chemical reactions going on. We have a lot of substances that are acidic and basic, and we don't want our pH levels to change very rapidly. So we actually have substances or molecules inside of us that act like buffers to help stabilize pH. And so the pH in most living cells wants to stay as close to 7 as possible because we have a lot of enzymes carrying out these chemical reactions. And if you get too basic or if you get too acidic, these enzymes are just going to get messed up and they're not going to work properly. So we want to make sure we keep the level of pH right where it's at so these enzymes can work effectively. pH can alter the shape of these enzymes, and as a result, the function doesn't work and they are useless. So chemical reactions produce acids and bases, and what buffers try to do is they try to keep the pH the same or level or basically the same, yes. So how do they do that? Well, they help resist changes in pH by either releasing H ions when a base is added, because remember bases take H's out, so what buffers do is in the case of a basic solution they'll add H pluses, or when an acid is added, because acids tend to give up hydrogens, those buffers will absorb those H ions. So we have a lot of buffer systems in our human body, especially blood. Blood tends to hang around the 7.4 pH range, also staying between 6 and 8. So we have lots of buffers, like hydrogen carbonates. We have some proteins that do the same thing, some hemoglobins that do the same thing, and hydrogen phosphates. But we have a lot of buffers in our blood to help keep our pH around that 7.4. All right, so I know I zoomed through that, but that is the conclusion of Chapter 2. What I need you to do is, if you have any questions, make sure you bring them to class tomorrow. I'm also going to post the water lab that you need to read before you come to class. Thursday and Friday are dedicated to you to finish that lab. If you finish it in one class period, go you. But yeah, that's that in a nutshell. Okay, so I do have 3 slides left, going back to my hypothesis, my chemical evolution hypothesis. So, water's unusual structure, okay, that it's bent, it's polar, it acts like tiny little magnets, as well as its properties, cohesion, adhesion, high specific heat, how it's less dense in solid form, they really play a key role in chemical evolution. So Earth, when it cooled, rain fell from the sky because, it was very hot and volcanic. So we have condensation that occurs and our oceans form. The planet's surface is dominated by liquid water. Rain and wind erode rocks. And then when it erodes rocks, it eventually finds rivers, and that river can carry those dissolved ions back to the oceans, giving oceans something to work with. Because remember I said atoms interacted with other atoms to form complex molecules, so this is kind of where this fits into that. So the oceans became saline, and then through that, those simple atoms and elements, simple compounds, they started to interact with each other. And so I think I will talk about the Urey-Miller experiment here pretty soon, about how the ocean was a prebiotic soup. And through lightning and redox reactions, we tend to form complex structures. So the environment from which chemical evolution proceeded was a salty solution of nearly neutral pH, somewhere around the 7. It did contain at least some compounds that helped reduce carbon atoms. So reduce means you gain electrons. And then thanks to water's high specific heat, the first products of chemical evolution were protected from further inputs of energy. Now, I'm not done with this story. I'm just scratching the surface of this chemical evolution. We're going to come back to this. But 2 things had to happen in order for chemical evolution to occur. First off, reactions had to involve very small and simple organic molecules, and then as a result to form these large molecules, and that these building blocks had to somehow link together to form the macromolecules of life. proteins, nucleic acids, carbohydrates. Okay, so the jump from non-life to life had to have happened when we got enough of these molecules to accumulate in the waters of ancient Earth. All right, that's college bio. Welcome. Yeah, that's the end of my TED Talk, as you guys say, right? Okay, I'll see you on Thursday. Well, most of you on Thursday.